Okay, so we were talking about different applications of Tutte polynomials and things similar to Tutte polynomials, and we're going to continue doing that today. I'm going to give you a quick preview. Not preview, because I'm not going to show you anything after this. A quick, what? View of knot theory. And of course, knot theory is also a very big topic. And we're basically interested in the aspects that are most similar to what we're doing in this course, matroids, Tutte polynomials, things like this. Told you I would keep you updated on where I'm getting my materials, so the place to read about this is a book by Welsh called Complexity, Knots, Colorings, and Counting.
Federico, does knot theory have applications to computers science in any way?
I'm not sure. I know knot theory is a very hot topic right now in biology because DNA is somehow, or in proteins somehow not around each other and so on. There's going to be an even better paper that you can read about this by O'Neill and what is your paper going to be called?
Sorry.
Untitled at the moment.
Untitled. So actually, this is the preview for so that you guys can then read their wonderful paper after this. Okay, so what's a knot? Well, you guys know what a knot is, and what you think is a knot really is a knot. And so I don't want you to be scared by this definition. A knot is an embedding of a circle in R3.
That last word, couching?
Counting.
Oh, counting.
Yep. So, the idea is basically that you take a string, like your shoestring, and then you kind of wrap it around in whatever way you want, and then you attach its ends. Okay. So take a string, some one-dimensional thing, wrap it around itself, move it around in any way, and then attach its ends. Okay. So that's a knot. That's what we're used to thinking of a knot. The only difference is, like a shoelace doesn't count as a knot because it's supposed to be a loop. So it starts where it ends. Okay. A link is just a bunch of knots that might be tied around each other. So it's an embedding of K circles. In R3. Okay. That's a knot, that's a link. And so the way that we are able to draw these things is through what is called a knot diagram, where basically what you do is that you just take a projection of your knot onto your view. So, if you look at it, it looks flat to you, and that's what you draw. So for example, here's a knot diagram. This is the first time I draw a knot in public. I'm kind of embarrassed, but kind of worked out. So you see, this is a loop that it looks like it's tied, right? I mean, it looks like it is a knot. You can't just untwist it. This is hard. Another knot maybe this one. So that's another knot diagram. Okay. But if you stare at this diagram, you're going to see that actually this isn't quite a knot, because you can, you can basically take this thing and undo it. You just have to flip this thing around, and then you get the unknot. So it's just a loop that is not knotted. Okay. So this guy is called the trefoil knot, and this guy is called the unknot. Okay, now.
But the unknot is in fact a knot. It's just sort of a trivial knot. Is that right?
The unknot is the trivial knot. So it is a knot because it is an embedding of a circle in R3. It's just a silly. It's not silly. I mean, it's just an embedding that is not knotted around itself. Okay. So that's how we draw these things. And actually, there's an exercise that I'm going to give you guys, which is that I drew a more complicated knot on the notes, and I'm not going to try to do it right now. But look at the knot, the third knot I drew on the notes. And I want you to basically see if you can unravel it. So is it the unknot, or the trefoil knot, or neither? I want you to do that. Okay. Now, of course, I have to define what it means for two knots to be the same. And as usual, there's a big word for this, which I don't want you to be scared of: ambient isotopic. That means the same. Well, again, intuitively, you're just going to think what you would think if you can take one knot and twist it around and get the other one. Okay? So if K can be deformed smoothly, to get L.
Do they have to be the same length?
No. So you're going to think that these are kind of rubber band knots that you can stretch out. And so you are allowed to stretch the thing out, move it around space, but what you're not allowed to do is cut it. So no cutting. Because if you're allowed to cut, then everything is the same. Actually, even that's not so clear. But I'm not going to allow cutting. You can't cut it out. And of course, you can't make two segments cross each other. No crossing. Okay. Now, the technical word is that there's a homotopy, blah, 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 homotopy between R3 and R3 that sends the first knot to the second knot. If that makes sense to you, then that's what it is. The intuition is this one. Okay. Now, the first thing that I should point out is that actually, in 1949, Fox noticed that there are knots that are incredibly complicated. When I say incredibly, I mean incredibly complicated, very complicated knots. For example, there are knots that you can't really draw in a piecewise linear way. For example, a wild knot, that's what they're called, wild knot, is one which is not equivalent, not ambient isotopic to any knot that you can form in a piecewise linear fashion. You would think that basically any knot you can kind of stretch it out and make it look like a polygon. But it turns out that's not true. There are knots that don't look like, that cannot be made to look like polygons. That is not, that has no polygonal, no piecewise linear representation. piecewise linear. Okay. And so, definition, a tame knot is basically the ones that we imagine to be knots that really, you know, if you stretch them in if you take the rubber band and take a bunch of points and just stretch it out, then it looks like a straight knot. It looks like a polygon. Is one ambient isotopic, let's just say, yeah, sure, ambient isotopic. Two, some polygon, some three-dimensional polygon. I think any knot that you can imagine is a tame knot. And the point is that if our theory allows for wild knots, then basically we can't prove anything because these knots are too complicated. And so people focus on tame knots, which are the ones that you're bound to encounter maybe in applications. And anyway, they're the ones that you can prove theorems about. So when people say knot, they usually mean tame knot. This is definitely going to be true for what I'm going to say today. But even in knot theory, a lot of theorems kind of restrict themselves to tame knots because that's where you can prove theorems. Okay, and so the big questions are basically if I give you two knots, in other words, if I give you two pictures like this, and I ask you, are they the same knot or not? Recognition problem. Are two knots the same? Or even the unknotting problem. If I give you a picture, is it possible to unknot it? Is a given knot the unknot? And these really are big questions, and they're open, actually. So there are algorithms for doing this, but there are no polynomial time algorithms for doing this. This is one thing that people don't know is whether that's possible. So open polynomial time algorithms. For these two questions.
But now trefoil knots can't be unknotted, can they?
And so that's the first question we should ask ourselves is, are these two knots really different?
Well, I thought that was part of the definition.
Well, so far I gave them two different names, but maybe they are the same knot. I haven't given you any evidence to, except your intuition. Your intuition says these guys are different, but that's a subtle question. I told you can turn a sphere inside out, so can you unknot the trefoil knot? Maybe. And in general, if I give you some picture, and the picture is too big, then no one can figure out if you can unknot this thing or not. All the algorithms are just too complicated. Okay, okay, so far this makes it seem like these are impossibly difficult questions, and that this theory is very hard. But fortunately, there's a very nice theorem that puts some order here. Theorem of Reidemeister. This is from 1935. Two knot diagrams represent the same knot. If and only if you can obtain one from the other by these moves. So you can obtain one from the other by what is called Reidemeister moves. What are the Reidemeister moves? Well, what is the first move that we did to that picture of the unknot to unknot it? Basically, twisted this part that is not knotted. So that's the first Reidemeister move. Is whenever you see this, you can just unknot it. You can just flip it around. Second is an even easier one, which says if you have a strand like this and a strand like this, well, then those guys are not knotted at all, so you can separate them. Okay. The third move you might think is more interesting, but actually it's not much more interesting either. Basically, what happens is this. If you have 3 strands of your knot, and one of them is on top of the other 2, then you can just slide the top one over the crossing into the other side. So now it's going to look like this. And now the crossing is up here. So I didn't do anything. All I said is that I have 2 strands here, and I have one up here, and I can cross this one over. So I didn't do anything to my knot. Okay. So it's pretty clear that these 3 moves are allowable moves. And what this theorem says is that actually you can tell if 2 knots are the same by this criterion, whether you can get from one to the other one using only these 3 kinds of moves. You have a question, Kim?
I couldn't slide it over if that the one going this way came on top of the back one. Right? It's that it's like 3 sticks. There's a bottom stick, a middle stick, and a top stick, and I can slide the top stick down. Yep. But if the bottom stick came
so what
on
you're
top
saying
of
is that if it's kind of like.
So if that connected through.
Let's see if I can draw this. I don't know if. We'll try.
No, I don't. I think your drawing is exactly right. That's all.
Yeah.
And that's fine. I think I can get it.
But I wanna make your point, which is a good one. That you might have 3 strands where. Actually, we have it right here. Here we have 3 strands. 1, 2, 3. So that the first one is on top of the second one. So if this is the first one, this is the second one, and this is the third one, then the first one is on top of the second one. The second one is on top of the third one. And the third one is on top of the first one. And here it's not, you can't slide
you can't do
one across the crossing of 2 and 3.
Right. And
you can only do it if they're the top one, the middle one, and the lower one, and you just take the top one and slide it through.
And what I was saying was, in just this little part of the picture you've shown us here, the lower one is clearly behind the top one, but it's also behind the middle one.
Yeah.
And you're saying it has to be behind the middle one as well.
Yeah.
Okay.
So you can't have the bottom, because right now it's like there's 1 stick, there's 2 sticks, there's another stick. So you can't have like these 2 sticks combining somewhere.
I mean, basically, this is a statement about pictures anyway. This is a statement about 2-dimensional pictures.
It's okay.
About knot diagrams.
Yeah,
Chris just answered my question in a much easier way.
Okay.
Thanks. He said if the bottom one was on top of the middle one, it would become the middle one, and the other one would be the bottom one. You're right.
Good point.
Thanks.
See, that's why he's writing a paper about this. Okay, so this theorem is very useful. Actually, I want to point out a historical fact here. That you should notice the 2 dates of these 2 theorems. This is from 1949 and this is from 1935. Meaning this theorem is older than this theorem, meaning Reidemeister proved this before knowing that wild knots existed. Okay? How wild are wild knots? They're wild enough that people didn't believe they existed. And they had proved theorems about knots, assuming that every knot is tame, because that's how we think of knots. And only many years later that people realized that actually there are these complicated knots, which really we need to discard from the game if we want to be able to prove theorems like this one. Okay. So So this theorem of Reidemeister gives you a procedure for showing that two knots are the same. So for example, if these two knots, the trefoil knot and the unknot, were the same, then you would be able to prove it to me by giving me some Reidemeister moves. But now the question I want to address is the opposite question, the question that Jack was asking, which is how do you know if two knots are not the same? How do you prove that? How do you prove that two knots are not equal? Okay. And you'll realize that this is similar to the question for matroids. If you wanted to show that two matroids were the same, you would just give me the isomorphism between the two. If you wanted to show that two matroids were different, then you could tell me, for example, well, this one has more elements than this one. Or you could tell me the top polynomial of this one is not the top polynomial of this one. So they can't be the same if they have different top polynomials. And this is the same thing that we want to do here, is we want to associate invariants like we did to matroids. So a knot invariant is a quantity that you associate to a knot that is the same for equivalent knots. Okay. So for example, what's a knot invariant? I should also tell you, I'm very often going to say either knot or link interchangeably. Remember, knot means one strand, link means several strands. So what's a link invariant?
Number of strands.
Number of strands. And that's maybe the only obvious one. But for example, what's a knot invariant? What do you associate to a knot? It's not so clear. But basically, this is the game we want to play. Is we want to try to investigate to find knot invariants that can tell knots apart. Now, when I say quantity, I say that vaguely, because this quantity might mean a number, it might mean a polynomial, it might mean a ring, so on. Okay. Many of the ones that people are most interested in, or many of the ones that people understand best, are polynomials. There's these new developments where they're starting to associate these really nice rings to a knot. But we're going to talk about assigning a polynomial. So here's a very powerful example. A very powerful invariant theorem. It's a theorem of Vaughan-Jones from 1985. And this is one of the theorems that people really like that Vaughan-Jones proved, and one of the reasons why he got the Fields Medal a few years later. He basically proved this. He proved that there is a polynomial now. This polynomial is going to have square roots and 1 over square root, so it's almost a polynomial, except you have some square roots. There is a polynomial not invariant V of oriented knots. Such that. What do I mean by an oriented knot? Well, the only thing I could mean is, a knot is a loop, and so I just want you to pick what direction you're going to walk around the loop. You either go forward or backward. Okay. So given a knot and an orientation on the knot, you're going to associate a polynomial in square roots. And this polynomial is supposed to have two properties. The polynomial of the unknot is 1. Okay. And the second thing you're supposed to satisfy is this. I'm going to write an equation. 1 over t times the Jones polynomial of, so we have a crossing like this, minus t times the polynomial where you have the same crossing, but now this strand is above this one. Should equal square root of t minus 1 over square root of t times the Jones polynomial of, now these two strands not crossing at all. This times this. Now, what does this mean? Might be a little confusing to you because I said I was defining an invariant of a knot. So V of a knot. But this is not a knot. Now, the idea is this. The idea is that if you want V of a knot, and you consider one of the crossings of the knot, then you're going to make two other knots. This knot is obtained by crossing these two strands, and this knot is obtained by separating them. Okay? So you get one knot where a little piece looks like this, the same knot except the little piece looks like this, the same knot except the little piece looks like this. For each one of them you have a polynomial, and the idea is that these three polynomials are supposed to satisfy this relation. Okay? And he proved that there is a unique polynomial that satisfies these conditions. It shouldn't be clear to you, first of all, that this actually defines a polynomial. Second of all, that this defines anything. It's not clear right away how you can compute a Jones polynomial using this formula, but we're going to see that you can. And it shouldn't be clear to you that this thing is well defined, because this is just defining some relations, and maybe these relations are redundant and in an incorrect way. So maybe by applying this equation in different ways, you get the equation 0 equals 1. But what Jones proved is that this is true. And the interesting thing is that actually this was kind of a, as I understand it, he wasn't exactly looking for a knot invariant. He was just doing some other thing on von Neumann algebras, and then this kind of popped out. And there's something to be said for objects that just pop out and you didn't construct them with your hands. They just were sitting there. Okay, so let's compute V of something. Let's compute the Jones polynomial of some link. And so this is for links also. For a link, this also defines. Excuse me. For a link, you also get a Jones polynomial. So what Jones polynomial would you like to compute? What's the simplest link that you can think of? Well, the simplest is the unknot, and we don't have to do anything there. It's a little bit too simple, right? V of this knot is 1. It's not so interesting. What's the next simplest knot that you can think of?
Figure 8.
A figure 8.
That's just
That's an unlinked.
a figure. No, but that's a good point. So how do you compute this?
Mm-hmm.
Well, what you say is this polynomial is not invariant. So because this guy can be untwisted to get this guy, and because this polynomial is not invariant, then this has to be 1. It's not obvious. I mean, it's part of the theorem that because these two guys are the same knot, you get the same answer.
You can calculate it. Just using those things and come out with 1.
Well, try. So exercise. Try calculating this using this. Calculating directly.
So what is this the unlinked?
So what's the next simplest link? Two linked circles?
Or two unlinked circles.
I think it's simpler to have them unlinked. So let's do that one. V of two unlinked circles. How are you going to compute this guy? You have to use this equation somehow. Okay.
Can you orient them?
You have to use this equation somehow. Now, this looks like which one of these three pictures? Well, it looks kind of like this one, but not quite.
Because it's not going the right direction.
Not oriented.
Because these guys are both oriented going up. Here, this guy is oriented going up, and this guy is oriented going down.
Can we fix that?
How can we fix that?
Turn it over?
Well, this is an invariant, and you can take this strand and flip it over, and now it's oriented in the other direction, and that can't change the polynomial because this is an invariant.
Wait, what? I thought you said it's an invariant
wait.
of oriented.
Oh.
Links.
Yeah, but what I'm saying is that this guy and this guy
Oh, because you
are the same link
Sure.
because you can obtain this one from this one by flipping over.
Those guys are really the same link. Actually, you don't have to flip it.
I told you I've never drawn these in public. Okay, these two are different, but you can get one by flipping it. So that's fine. So now we have this guy, and now this looks a little bit like that. Now we have this section that looks exactly like the thing on the right. And that's what we're going to do. We're going to say V of this, where these guys are like this, times this thing equals 1 over t, v of something, minus t, v of something. What does this guy look like? Well, what you do is, again, we're zooming in here, right? So you leave everything else alone. Okay. And then the green stuff, you flip it according to what the formula over there says. Okay. So this formula says cross this one on top of this one, and cross this one on top of this one.
But those are both your figure 8.
But this is good news because these guys are both the figure 8 knot, and Jack pointed out to us that these have Jones polynomial 1, and so therefore this is 1, this is 1, and we get this, and therefore what we were looking for is this divided by this, which doesn't necessarily look like a polynomial in square root of t, and 1 over square root of t. But the nice thing is that actually, this is a difference of squares.
Right.
This is the square of this one. This is the square of this one. So actually, this is just this, which is a polynomial in square root of t, and 1 over square root of t. Okay.
Why is it negative? Oh, yeah. Thank you.
So that's how you do it. That's how you compute v of two unlinked things. And we just proved a theorem, a great theorem, that two links are different from one link because they have different Jones polynomials. But now we didn't need to do that because number of links is an invariant, and this guy has 2 links and this guy has 1 link. But that's a proof. Okay? Now, the exercise that I want to leave for you, and I really want you to do this exercise, and I think you're going to find it a fun exercise, is to do this for the trefoil knot. Now, what does this look like again? This. Compute it. Show that it's not 1. And by showing that it's not 1, you're going to show that actually the trefoil knot and the and knot really are different and they deserve different names. Compute and prove that the trefoil is not equivalent to the unknot. Okay. So fun exercise. I had never done this before, and I did it before class, and it's nice. And actually, the other thing that I want you to do is to think about the 2 orientations. So these are 2 exercises: computed using this orientation and computed using this orientation. The left hand and the right hand trefoil. And right. I want you to compute those 2. They look like they're the same, but we should make sure that we get the same answer. Okay. So that's good. That gives you an idea of how you compute these polynomials, although at this point it shouldn't be clear to you that you can always do this. I don't think it's so clear. Okay. But now let's talk about another way of doing this. Let me draw a knot again. And again, let me choose it to be the right-handed knot. The right-handed trefoil. I guess the reason they call it right-handed is because if you do it with your right hand, you do it differently than if you were to do it with your left hand. It would look different. I mean, if you look at it in a mirror, you're going to see that it looks different. And the question is, are they topologically different? Okay. What I want you to notice is this. And actually, let's draw a more complicated knot. So maybe here, I really don't know how we're going to do it. Okay, so there's a knot. It's not too bad. I want you to notice something. And what I want you to notice is that you can give the regions like they're a checkerboard. As a checkerboard. I'm going to color them black and white. And, so for example, let's say that this one is black. Why like a checkerboard? In a checkerboard, whenever you go to a neighbor, it's the opposite color. So you go black, white, black, white, black, white, black, white, white, black. And the point is, any two faces of this picture that are joined by an edge have opposite colors. You should think about why you can do this, and it's true, you can always do it. Okay. And so maybe the link, the diagram I started with, I would call it D, and I'm going to make a graph. What I'm going to do is I'm going to put a vertex in each black face. Okay. Now, this is a little bit similar to making the dual graph, right? And in the dual graph, what you do is that if you take two neighboring faces, then you join their vertices. But here there's no neighboring faces because no two black faces are neighbors. But what neighbor might mean is that they share a vertex. This is the closest we can hope for. And that's what we're going to do. Whenever two faces share a vertex, you're going to join them. Okay? So these two faces share this vertex. I mean, a crossing is what I mean. So these two faces share a crossing, so you make an edge. These two faces share a crossing, so you make an edge. These two share a crossing, so you make an edge. These two share this crossing, so you make an edge. And these two share this crossing, so you make an edge.
Is that going to get two?
Did I? And there's more. Because this guy and this guy also share this one.
Yeah.
And this one. Yeah. And this one. Is that it? That's it. So this is going to be the signed graph of the diagram. Why signed? Because I'm going to put signs on it. And the way I'm going to do this is basically that there's two kinds of crossings. Let me make sure I do this correctly. I do the same thing twice, didn't I? What am I going to do? It's kind of a right-hand rule. So you're going to go from the upper strand, and so from the upper strand, you cross through the black region to the lower strand, and then see where your thumb is pointing. So here from the upper strand to the lower strand, you go like this, and the right-hand rule tells you to point this way, which is a plus. So this is a plus crossing. And this one, if you go from the top strand to the bottom strand through the black region, you go like this, and you're pointing toward the other direction, the minus sign.
Oh, I see.
So it's the same thing as when you're teaching vector calculus to your students, and it's confusing at first, but you'll get used to it. Right? Just the same right-hand rule. If you go like this, from the top through the black region, and see where your thumb is pointing, outside of the board is plus, inside of the board is minus. Okay, so what's this one? Here, minus. Here,
Same.
minus, minus.
Wait,
Plus.
wait. The third minus is the plus.
Oh yeah, plus. That's good. You guys got it better than I did.
Minus.
So this is a minus, I think. This is a plus. This is a plus. And this is a minus.
Wait.
Maybe.
That one.
This one?
No, the one down. Yeah.
Yep.
I think
This
that's
one
minus.
is a minus. No. Minus.
Because you went through the white region, not the black.
So it takes some practice to do this correctly, and you do it correctly. Because you go from the top through the black region, and you're pointing into the board. There might be some mistakes because I'm trying to do this quickly, but anyway. I hope you get the point of how you do this, and you can do it correctly with you, taking your time.
It appears to me like there's two different possible black and white colors. You could just invert this whole thing,
Right.
and that would give you a totally different graph.
Absolutely. You can make two different colorings. The other coloring you could make is just flipping the two colors, black and white, and you would get a different graph. And I think in knot theory, the convention is that the outside region is always black. Okay. But of course, whatever I prove about this is also going to be true about the other coloring. Okay. Okay, now let's do this for a simpler knot. Favorite knot, okay. Except I think in my notes I followed the wrong convention, but
So the middle is.
here there's only two vertices. And if you do this, you're going to see that they all have the same sign. Okay.
So they're all negative.
They're all negatives.
but yes, otherwise.
They have the same sign, negative. Okay. When does this happen? When do they all have the same sign? I'll let you think about that. Think about why this is true. It happens when, as you walk around, you go over, under, over, under. So you see here I'm going over a crossing, under a crossing, over a crossing, under a crossing, over a crossing, under a crossing. It's called an alternating diagram. Alternating knot diagram. You go over, under, so on. And if so, then you just get a graph. And actually, if you think about this a little bit, you'll see that this is a bijection between alternating knot diagrams and planar graphs. So if you start with a planar graph, you can see that you can make a knot from it by reversing this procedure. Okay. Now, again, for many, 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 many years, people assumed that every knot was alternating, meaning that any knot that you could draw could be, this is not an alternating representation of this knot, but there was this conjecture for many, many years that you could take anything, any knot diagram, and change it into an alternating knot diagram. Turned out not to be true, and the smallest example is big, which is why people hadn't noticed. But the point is that all the small knots can be drawn alternating. Knots means, small means at most 7 crossings. So the first one that cannot be drawn like this is a big knot that has 8 crossings. Okay. Theorem. Suppose that D is an alternating knot diagram. And G is the graph that you get. Then, if you want the Jones polynomial of the knot, you compute the top polynomial of the graph. This is amazing. But that's what it is. So now, this is what you do. You have to do, as you know, there's always some garbage associated to this in front of it. So -1 to the number of edges. I'll tell you what A is in a second. 2v minus 4e minus 2. Then you I'm going to simplify this. I'm going to try to simplify it on the spot. We'll see if it works. That's it. So the Jones polynomial is an evaluation of the top polynomial. And what this means is that this very complicated procedure for computing Jones polynomials of knots is something you might be comfortable if you have practice with it. But if you're not comfortable with it and you prefer computing dot polynomials, then that's what you do. And as I understand it, people seem to think this is the best way to do it to date. Is just draw the graph, compute the dot polynomial, and then that's it. Just plug this in. All right.
Let's go to the first talk, and then I think so. That would work for me. Wow, look at all these black markers. Little black marker graveyard or something. So,
Yeah.
Federico?
Actually, I'm going to talk to.
We're going to turn in our papers by the 25th. Are we going to have an opportunity before then to hear from other folks about their papers, other than informally? But
Probably not.
okay. Bug them afterwards.
I mean, if anybody finishes ahead of time, then I'll
Right.
I'm going to post all these papers on the website. So
Right.
as people finish, they'll go up. So
Yeah.
the two of you finish first. Everybody will get a chance to see.
Right.
But I like your write-up. I think you guys are totally on track. Sounds good.
Okay. we hope that what we're doing matches what we wrote.